Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. My name is Tandy Trower. I'm the General Manager of the Microsoft Robotics Group, and it's my pleasure this morning to introduce you to Rod Gruppen. Rod is from the University of Massachusetts at Amherst. You'll see I won't read through what you already received as Rod's extensive background. I think it's probably best to kind of summarize it as saying that he probably has one of the best jobs around there is in terms of what he gets to do in terms of putting all his working knowledge in terms of physics and mechanical engineering and computer science together to build robots. He's visiting with us for a few days. He and his team is visiting with us a few days here at Microsoft. We're doing some integration work on between what he's doing and Microsoft Robotics Studio. But this morning he's going to tell you a little more about what his project is and what his group does at the University of Massachusetts. And I think it'll be very exciting. He's going to give you a preview or show off his robot to us as well. So without any further ado, I'd like to introduce Rod. Rod, thank you for joining us today.
Thank you. The real reason we're here in Redmond today is because of this robot and some work that we're going to do locally with the Robotics Studio people. I'm going to give a talk related to why we build such robots, and at the end I'll talk a little bit more about what we're doing with this one. I've entitled the talk Developmental Programming and Distributed Robot Control. I put an asterisk up there because when you see distributed control, you might think of sensor networks and large-scale deployments and things like that. What I'm going to propose is that distributed control is really more ubiquitous than that. It's something that all control devices, processes that are in manufacturing, processes that describe the computational architectures of biological motor control, neuroscience and neurology, are best represented in terms of distributed computational models. So I'm going to talk about that, and mostly in the context of a walking platform, a bimanual dexterity platform we call Dexter back at our lab, and this guy. No sensor nets made it into my talk because I was getting too long, although we run those too at UMass. But the asterisk is to make sure that you understand when I talk about this robot, I'm talking about distributed processing and the interaction of many processes that reside simultaneously, concurrently on the machine, as well as many processes that are external to it and happening in the environment. So here's an outline for the talk. I'd like to first overview why we came to this model. The sensory motor development in human infants is really very remarkable. If you haven't seen it before, it makes a very strong case for why the control processes, the way you configure them, the way that they come online and the way that they disassociate later is very much responsible for how our brains mature cognitively into adulthood. And robots that are, for instance, in elder care applications or exploring Mars or something like that cannot be programmed in the ways that we have traditionally programmed software. They must react to new challenges as they see them and build new models and alter their software. They might even want to ship some of their software over to adjacent robots to help them solve problems. In order to do that, I'm going to talk about the control basis architecture in which we have a substrate that is an embedded control mode, access methods to those controllers that consist of protocols for managing sensors and effectors. We have a middleware layer, and we've used all of these. I'll talk a little bit more about this before. We started with backplane DMA. We tried ScramNet, which is just a reflector, an optical reflector from backplane to backplane. We still use that a little bit. We tried Genie. We tried Player Gazebo. NDDS, NASA uses, so we tried that too. And none of them are very satisfying as a middleware alternative. We're here now in Redmond to figure out how to do the Microsoft Robotics Studio and apply that as a middleware layer in all of the applications we're building. And then the task level, the application layer is represented by this control basis idea, and I'll talk a little bit about that. But the heart of the talk will be this developmental assembler, the idea that you can actually guide a robot that interacts directly with the environment through a sequence of developmental problems that can acquire knowledge structures that it reuses again to write new programs, and that you are essentially embellishing temporally extended instruction sets for robots which grow over time and do more and more comprehensive behavior. The examples I've already talked about, learning to walk, manual dexterity, and then this guy in mobile manipulators is where I'll end. I want to try to make the case for why the future of robotics is really in robots like this. Small commodity robots, inexpensive, that do lots of work and can move and manually interact with the environment.
We can elicit the Moreau reflex by having...
This is an infant.
Relax, unsuspecting.
I'll let the narration speak for itself.
Stimulus, and there's a good Moreau. Quiet and headline, midline. And then just get a stimulus of dropping him back a few inches. And that's a good normal response. Okay.
A newborn
We're going
infant.
to look for Moreau. At this age, he may...
That was newborn. This is 3 months.
But okay. Okay. He's lost his Moreau at this point in time, and it's usually this time that they do lose the Moreau. So he doesn't have a Moreau, so that's good.
All right, so this is a neurologist speaking, and they look at the onset of these reflexes. These are built into the spinal circuitry and the cortical projections in the brain from birth. They develop in utero, and then they act to bias the sensory motor system in a particular direction. So for infants, they emerge 8 to 9 weeks in utero, and they're inhibited by 16 weeks. This is a clasping reflex. This is a reflex that allows the infant to, if you go back to our ancestry, to basically, in response to a vestibular instability, to open up its arms and grab the hairy back of its mother in the trees, right? And make sure it doesn't fall to the bottom, stays in the canopy. And it's very much responsible for helping the infant survive in order to learn anything in the first place, first step, right? So these are very primitive. After 16 weeks, it transforms into a more adult-like startle reflex. If you hear a big bang in the room, everybody will kind of go like that. That's the descendant, the antecedent of the Moreau reflex, having been integrated into a lot of other behavior. I'm making the case about children because this is the only way that I claim intelligent sensory and motor systems actually do mature into adult, autonomous, independent agents that can make independent decisions and deal with environments they haven't ever considered before. This is another example. This is one that I'm particularly interested in. It has to do with palmar grasping. You're all, if you have children, you're familiar with this.
We can elicit a grasp reflex by again putting the hand right there in the thumb, and again the baby is able to grasp. We can open the hand by stroking the side of the hand, and then just stimulating a grasp reflex just by again putting the hand right there and have a grasp reflex. Okay.
You've all seen this.
There.
You can actually pick children up,
grasp reflex there.
having stimulated the proper grasp reflex at very young ages.
And then lift the baby. If we can get him to be quiet there, you can see he's almost pulling himself up as far as the grasp reflex and able to hold on with that hand. As far as just putting pressure here at the ball of the
It's
foot.
also related to that
inflection.
legacy we have from the canopies reflex that applies to the feet. And if you stimulate the ball of the foot, you'll get the toes to curl over and try to grab that thing as well.
You can see that there's a grasp reflex. As far as a grasp reflex, still has...
So if they have abnormal persistence, so these are, let's call them preconditioning filters on the input and output stimulus response of the infant. And if you use them as filters, you bias the developing cortical projections to look for relationships and associations between certain signals and others, and ignores the vast majority of the information that's coming from the world. And this allows the infant to program its sensory motor responses in a sense. If they have abnormal persistence, they can delay manual dexterity, hand-to-mouth coordination, swallowing problems, and remarkably, they delay speech. So this might be anecdotal at this point. There's not too much evidence to support strong conclusions in this regard. But your ability to start interacting and forming categories in the world, what environmental affordances afford grasping behavior, for instance, That leads to the production of nouns about the objects that you're grasping and adjectives to describe their differences between different objects. And so starts to lead to a kind of linguistic category that describes those interactions with the world.
Looking at
this is the Babinski, and I'll truncate this discussion a little bit. Babinski is one that persists. The neural substrate remains. Cortical projections inhibit it. So this infant, you will see if he strikes that side, strokes this side of the foot, will do a splay the toes this way, right? Now, if you fall off your motorcycle or your bicycle or something like that and bang your head, the neurologist will do the same thing. And if they stroke your foot like this and your toes splay like that, that's big trouble. That means that some inhibitory cortical projections have unmasked this developmental reflex again, so that whatever tissue had been lesioned in the trauma ceases to behave as it should in a mature adult and reveals the kind of underpinnings of this developmental system. This one I'll skip by too, just to mention, if you turn an infant's head, he's laying on his back, supine on the table there. If you turn his head to the side, it will extend arm and leg on the side you turn the head to. If you turn it to the other side, it will flex these and extend the others. It has a lot to do, as you can see, with maybe getting down the birth canal, unobstructed airways. This is crib death kind of ideas. This is a reflex to try to minimize that. It also extends the focal apparatus to point at the hand. And they believe it's one of the big kind of initiators, catalysts of hand-eye coordination. So if there's a reflex that constantly puts your hand in front of the visual system, then your ability to get a good proprioceptive sense of where your hand is relative to your eyes starts to be programmed. Also something a robot should be able to do. Now, let me just, a small tangent. Roboticists already know how to write the equations to do all this stuff. Why should we do this? And what I'm going to propose to you as this talk builds into more complicated applications is that if a robot has good common sense knowledge structures about how its own behavior affects the stimuli it receives from the world, it will be able to react in intelligent ways in new situations it hasn't ever encountered, or that the programmer has not written the equation for. And that's the whole point. This one is the positive supporting reflex. Let's see if I can get this one to play, because everybody smiles when they see this child.
Stand up. Let's go ahead. Let him sit up.
If you put stimuli on the bottom of the feet of the infant, they will extend the legs and try to prop themselves up in a kind of a pillar-like stance. And this is very much, the thing that's striking about this example is that they like it. It's fun. When they exercise these kind of pre-programmed tendencies in their neurological organization, it releases dopamine in their brains and they smile. They like it. So their body is not only given these initial kinds of responses to the world, they're also pre-programmed to really like it and want to do it a lot. This is, they're all playing simultaneously.
Push the head down, the feet go down.
Kind of a cacophony. This one is the most robot-like reflex you can see in an infant. You hold them on the stomach, they go like Superman. You push their head down, their legs flex down.
5 months of age, so he has.
Now, I don't know really what this is for developmentally, but you can see that this is a machine. This is a robot, if you will. I don't mean to demean infants in any way, but we are a machine, and we have a very sophisticated neurological, sensory, and motor organization. Can we build that kind of organization into robots and then provide analogs of the processes that turns that infant into an adult? If we can do that, then we have a machine that participates in its own programming, is parented, and the programmer becomes more like a parent than somebody who sits at the keyboard, and we end up with robots that mature and can transfer that knowledge onto other robots. All right, with that, I just wanted to emphasize that by watching I've compiled a chronology. Here's birth at about 10 months. This is from point of conception. This is in utero, and then after birth. And you can see that these reflexes, like Moreau, some of the ones we've talked about, they start and they end. And the normal development of a cognitive organization starts and ends according to a very reliable pattern. If you depart from this pattern, you have developmental delays and need intervention, essentially, in order to compensate for what you missed in your experience. And what isn't pictured here is that some of these actually, they start to persist out to here, but they die and they go away. They've served their purposes and they atrophy, and you can't elicit those responses anymore. And then certain others develop out into adulthood. So you get this sense that there is a non-stationary programming environment, one in which the instruction set changes. It's there to make certain important cognitive concepts conspicuous early in your life. And having acquired that knowledge in your environment, right? So we can be on the polar ice caps, we can be in the rainforest, quite different environments that we have to be able to adapt to. We only have a blueprint for responding to those environments. We imprint on those environments, on the people around us, on the society that we're part of, and then we build new programs that reflect all of that organization. This is, in fact, a trace that goes from a prone position to a bipedal toddler stance. And Patrick Deegan, who's in the audience, and I'll talk about a little bit later, is doing this on this robot, which also has a dynamically stable, the potential to be dynamically stable like a biped. But the programming experience for this robot can follow very much the same kind of a structured, discrete programming sequence like this. All right, so what's next in children? Well, they start to worry about, after they master how their bodies work and their relationships to primitive stimuli in the world, causality. They form categories. When they start that postural stability track to the point where their hands are free, an explosion of manual dexterity activities start to happen. When that explosion of manual dexterity starts to happen, an explosion of linguistic activity starts to happen. So you can see one kind of bootstraps the next. When their hands are free and they can balance on their feet, they start exploring with their hands. When their hands are exploring, they start labeling linguistically the things that they're interacting with. I feel very strongly that hands are the key to figuring out how our brains work, what makes us distinctively human, and that language is just an artifact or a part of that process. We get to animacy, intentions, spatial representations, time, and numbers. The things that are in red here I'm going to speak to in the context of our architecture and the kind of platforms we're using in subsequent slides. So here's that analog I was talking of. First of all, we have a substrate. In the next slide, I'll talk about what that substrate really means as an analog to human beings. But it's sensors, motors, distributed control, and methods for accessing the status of those distributed controllers. Then we have this middleware I was talking about before, and the robotics studio is our current middleware part of the architecture. A task-level control basis, which I'll describe, and then developmental programming. And that's how I'm going to proceed now. The rest of the talk is going to be related to the computational architecture, not the biological inspiration. All right, so here's what this motor unit is. This was recognized way back by Descartes. If you put your hand in a fire, you will respond by withdrawing it. That will happen before your brain gets the signal. Neural processes propagate electrical voltages at a measurable speed and is relatively slow, between 10 and maybe 100 meters per second. So when you stick your hand in that fire, pain receptors that are on the tips of your fingers actually go back a spinal nerve through one segment of the spinal cord and then innervate flexion in the muscles and get your hand out of the fire. There's firmware in your body. It keeps you alive. It keeps you from damaging the fingers you're going to need later to start constructing all those nouns, is the idea. Those are called motor units. Alpha gamma motor units are typically what happens, and they form a particularly important part of our architecture. So this is the computational model. Let me start over here. These are the motor units. If you're a control theorist, this looks like a simple closed loop transfer function, and you can represent it as such. In this robot, it's implemented in 12-channel FPGAs that do closed loop position control at 2,000 hertz, something like that. Dedicated machines that talk about how motors, muscles, innervate kinematic devices. The control basis resides right here. It is a Cartesian product of three different parts of a closed loop control. The artificial potential function, right? So gradient descent on this potential function is our control inputs for the motor units, is the idea. And the potential function is constructed with respect to a particular stimulus pattern and affects a certain pattern of motor or effectors. So if you plug these together, you find an artificial potential, the means of assessing your status on the artificial potential, and a means of descending that potential. And that becomes a closed loop. This is closed loop down here too, right? This becomes a slower bandwidth, hierarchical closed loop control. In terms of this thing, phi, the artificial potential, which is like the intention of the system. I intend to optimize with respect to a particular objective function. All right, so now what happens is we watch those controllers. This is a very big space of possible controllers that you construct. In fact, we start with a developmental stage which first limits the range of phis and sigmas and taus that you're allowed to explore. So this is like the child with blurry vision or low frequency hearing as they emerge from the womb, right? That's not just because your body didn't have enough time to mature, and it would obviously be better if you had high acuity vision. It's throwing away extraneous information that would only confuse you. It would only delay your development. It's focusing you on a few features and saying, what do you find in associative relationships between these kinds of signals? It builds a little program, and it keeps that program. Says, I understand the relationship between that subset of my state space, and with that knowledge, I can now try to attack the more complex real world. So that's the developmental stage. And we build those. That's the programming interface now to these guys. The rest of the structure is all built and native processes in the robot. These build these control basis closed loop responses. The potential function and the rate of change in the potential function is an activity modeling, enters this activity modeling block. And what we're doing there is things like hidden Markov models and abstract hidden Markov models, and such is the case when you're doing speech recognition and things like that, or any of the other activity modeling activity which is popular in the literature right now. And you characterize what's going on in the world by virtue of how signals are changing in response to controls that you've constructed, right? So I like to talk about the rabbit and the wolf. The wolf is trying to catch a rabbit, and he's watching his head pan and tilt as he's trying to track visually where the robot's zigging and zagging, right? If you can get the potential function to go to 0, it means you've closed the gap between the wolf and the rabbit. If it doesn't go down to a place near the origin of that plot, it means the rabbit is successfully eluding you. This is all very important information to try to figure out what you should do next. Okay? So we model activities as the robot interacts with the world, and those activities become a situation which we're going to use as a surrogate for state information in graphical models like Markov decision processes, where we can do reinforcement learning and all kinds of fancy adaptive optimal stuff. So we build a very structured space. We hook up Cartesian products of that space to try to do experiments, closed loop experiments in the world. We model those experiments. We use the status of those experiments to apply these situations, and then we use reinforcement learning to attach a value function to it. One of the important hierarchical abstractions that's possible with an approach like this is this very striking relationship between these little artificial potentials down here, which are like intentions, like objectives, and value functions. They both have the property that greedy descent on these functions yield optimal behavior. All right? So once I build those, I can stick this construction. This is a transition policy in a discrete event system. Right? I can stick it down here. I can associate sensors and effectors with it, and I can do more experiments. Is there an object in this room that I know that will provide the affordance of graspability? Right? As soon as I know how to grasp, I can start that experiment and find out that that cup is, that plate is, this table is probably not, given my finite resources, right? So I start to be inducing categories with respect to hierarchical behavior. So the way that this goes about learning is we set up a developmental stage. It does, let me flip through the slides here and let you just watch the progression. I set up a developmental stage. I then stochastically sample, I explore, I put the Cartesian product together, and I start interacting with the world through it. It forms combinations of things we can call controllers in the control basis that interact with these lower level motor units that are part of the robot. We model its activity. We build the structured Markov decision processes. We generate a value function on those Markov decision processes. And then we have this thing called a schema, which is in psychology and in AI. And it is a patterned plan or template for a general class of actions that you're going to do with the world. The schema, as a data structure with formal properties, gets loaded back into the control basis, and now we have temporally extended instructions that we can also explore by stochastic sampling, and we keep going. Now, there's a lot of work in our lab about intrinsic motivation. How do you get this system to just kind of, disavow the trivial solution, which is to sit quiet and not explore anything? There's no penalties involved with that. You don't use any energy, right? But there are intrinsic motivations in humans and thus in our robots as well for not being quiescent, but to actively try to find models and explanations for them and controlled transitions that it can rely on, that it can generate of its own free will. All right, now if you want to use one of these schema, you just use its value function, and you just do the argmax. If that's the situation in and that's the actions, and the value function is a function of those two parameters, then you just pick the actions that maximize the value. And so you just act in a greedy way, and you can act just like a controller again, but it's an underlying hierarchical discrete space. All right, so here's an example. This was Thing, the first example we did. It's a little servomotor, four-legged, 12-degree of freedom quadruped. We have a resource model that allows us only to allocate in terms of effectors, tau, 4 legs, not the individual joints in the leg. And as a result of a design I'm going to talk about in a few seconds, it led to 2 to the 13th states and 1,885 actions possible from each state. Just as a margin note here, we allow concurrency even at the continuous time level. If you have an artificial potential in the form of a bowl structure, and your policy is to descend it greedily, then you want to go down the gradient of the bowl. That also means that there's an isolevel curve around the bowl that says you didn't make any progress towards the bottom. Right? It's orthogonal to the greedy descent. And so if you're going to go greedy on this bowl, another bowl can tell you another action to go in, and you project that onto the isolevel curve. It means it doesn't destructively interfere with the first priority controller at all. Right? This is formally expressed in terms of Moore-Penrose pseudo-inverses. Was developed by Yoshikawa as a roboticist in the 1980s. And what we've done is really embraced that idea and said if you express everything as value functions or potentials, then you can combine every form of behavior in these strictly non-destructive hierarchical organizations. Very powerful, and I don't want to leave that out, but I'm not going to talk too much about it in the rest of the talk. So we have 4 legs, we have X, Y, and theta configuration of the body. We have 4 legs, X, Y, and theta configuration as possible abstract effectors that we can change the values of. And we have something that's going to do moment control. If you're familiar with bipedal humanoids, most of them use this thing called zero moment point controllers, where they just try to build a quasi-static polygon in the supporting structures of the feet. And if the center of mass of the robot falls into the interior of that polygon, then the robot will stand there of its own accord. Right? Not dynamically stable, but it won't fall over. And if you lean forward and the center of mass goes out of that polygon, then you're unstable and you've got to watch out. So we have a moment controller that just takes all the moments generated by contacts between the feet and the floor and wants to sum them to 0. And it's a form of zero moment point control, and we're doing it for this robot. The difference is we allow the system to explore combinatorically the different combinations of legs that can build those kinds of polygons. And kinematic conditioning. A kinematic device, as you all know, can do forces and velocities anisotropically. My leg is a good example of a singular configuration of a kinematic device that is designed to support my torso's mass above the floor. But it can't really generate velocities radially from my body anymore in that direction. It does them very well in this direction. So I can run and I can hold my weight up. Very sophisticated and elegant design. So because kinematic devices are not spatially isotropic in terms of their velocity and force capacity, we need to figure out how to apply velocity and force capacities of a particular configuration to a task, and that's what that does. A lot of this is in papers that you can get more details out of. I'm going to be somewhat superficial in this talk. All right, so we construct a set of controllers. That's the moment control. This is kinematic conditioning. Moment control is allowed to be configured by taking as the input sensor stimuli any triple of legs, any tripod, because a tripod is the minimum stable configuration, right? And it can descend in order to try to stabilize the platform by taking one of those legs and moving it to a new location. When it hasn't converged, it asserts a predicate value of 0. When it has converged, it asserts a predicate value of 1. It says that tripod is now a possibly stable tripod, right? The kinematic conditioning takes all 4 legs and it moves the heading of the body so as to move all 4 legs simultaneously back towards the middle of the space where they're isotropically conditioned, forces and velocities equally well in all directions. That's it. Those are the only 2 instructions I'm going to allow this robot to explore in this developmental stage. As a result, we get 1,885 possible control combinations by allowing 1, 2, and 3 of those to be chosen concurrently from the set of 13. Right? Because if you allow all of these permutations, you get 12 out of that and 1 out of that. That's 13 controllers. Nest them 1, 2, and 3 deep. Add them all up, you get this many. The discrete events is the 0, 1, 2 tripod stable? Is the 0, 2, 3 tripod stable? And so on. So all I'm doing here is saying you must assert predicates, summarize the dynamic status of this robot by determining what combinations of legs can currently lead it into a stable configuration. There's no task yet, right? I haven't said anything about task. This is just a very structured, minimized, very succinct, tiny little corner of the state action space and 5 predicates. That is 32 combinations of things that the robot needs to be aware of. I can put logical constraints on this. So I can overlay my own neurological organization by looking at the predicates. The same thing that says pull your hand out of the fire before your brain knows can say you may not try that or I'll fall over. And it can do it before the level that's trying to learn anything has to be aware of it. So the first one is at least one of the stable tripods must be true at all times. Right? Don't fall over. Single trial learning, no reset. You don't go pick this robot up and put it back on its feet. It's got to learn in a single trial. This one is a little bit more abstract, and that's designer influence. It says, I have to mime this one. It says, if my center of mass is currently in the interior of this tripod, this polygon formed by this tripod, it can't simultaneously be in the interior of this polygon, no, that polygon, and yeah, leave my hand there, move my foot, that polygon, right? So there's a line from that foot to this foot, and the center of mass is on one side or the other. It can't be on both. That's what that says. That limits the number of states and actions that are actually legal in the system. That reduces it to 32 states and an average of 157 actions per state, which is reduced by 99.94% from the initial expressive power of the control basis. So what we've done is by applying just simple little resource model and 2 little logical axioms, identified just a tiny little corner of the state action space permitted by the control basis. And in that little corner, we're going to try to do stochastic exploration to find out if we can write new programs that are meaningful to the robot. And this is trivial. This is an old experiment. This will go by rather quickly. That is thing from the top. And what you're going to see initially is the first maybe 15 seconds of the stochastic part of the exploration within the legal corner of the state action space, right? Won't fall down. And then it'll flip. You'll see this number change to about 11 minutes. And then it'll show you what the greedy policy was that it learned. Okay, there it is, stochastically exploring. And that's a rotate gate. And so what we've done is we've conspired, without the knowledge of the robot, to build a state space in which it was like falling off a log to find a gate that I think the robot will find useful in the future. This is not part of its genetic inheritance. This is something I, as a programmer, told it it should explore that space. You'll find something useful. It puts it away as a temporally extended action by using that relationship between artificial potentials and value functions. That's the program, by the way. These are the actions. These triangles denote null space projection. So this is a primary controller, that's a secondary controller, that's a tertiary controller. This one must project its inputs into the null space of this one. This one must project its inputs into the null space of this one. So the primary controllers are guaranteed to be protected from destructive inputs from the subordinate controllers. These are the actions that go around this central 4-step gate. 95% probability if you're in this state and you enter that action that you'll go to this one, and so forth. The green denotes transition probabilities in excess of 95%. The blue ones are lower probabilities and less frequently visited states. And so if you were to bump into a curb, it would take you off over here someplace, and the greedy policy gets you back into the main cycle. So it's a program with contingency plans built around what it explored, and it's now a macro, and we're going to call this a controller, put it in the control basis, and say, if you'd like to configure that controller and use it instead of the primitives, go ahead. All right, so now that program is this kind of a transition model, and we've done something to factor it. There's a declarative part and a procedural part. And what we've done is we've factored the two apart. The declarative part is the fees, the objective function. The procedural part are the sensor and effectors you had to use. So we said, well, there's one instance we know that this sequence of objectives yields some useful work. And then we have this procedural part. We say, that's useful in this context, and maybe it will be the same plan, the same schema will be useful in another context if we use different resources. Now, that's an abstract idea. I'll show you what I mean by it in a second. And you end up with a schema now. From a single sensory motor program, you hypothesize the existence of a schema, a general plan, a general outline. And it has the procedural and declarative split up. What does that mean? That means when I give that program to this robot, who also has 4 independent limbs and can interact with an object, it executes that behavior. That's a rotate clockwise, rotate counterclockwise, and it's only doing the walking gait that the first robot programmed in its context. And what we see is there's another assignment of resources to that. The procedural details of that declarative schema can be swapped out. I can give it a different 4-legged robot. It should do the same thing. I can give it a 4-legged hand, a 4-fingered hand, excuse me, 4-limbed, and it will do a rotate gait too. You can search now. Once you have a schema, the declarative part, you can search for different parameterizations of the procedural details. You can decorate the schema differently and see whether the transition probabilities are satisfied. And if they are, you have another instance of the same general plan with a different robot to different effect. Now, we learned rotate. It took 32 states, 157 actions. We did it many, many times. The result was the same. It was a very stable learning problem because it was so small and well structured in 11 minutes. We then start a step 1, which is like the bipedal gate reflex. We added the primitives. We added some more primitives, which made the state space bigger. We added more primitives in the rotate macro. That made it even bigger. Now, if you had no marginal impact of the control knowledge you acquired in the original macro, everything should slow down because you're just a bigger space. But what we found was that with the policy, this one, the most complicated design that we had that had the rotate macro built into it, within 2 hours it was doing better than the primitives without the macro alone. Within 8 hours it was doing about twice as good. And so what we found was if you bootstrap the system by putting little chunks of knowledge in the right order, that subsequent problems become easier and easier. Go a third level. Now we know how to rotate and we know how to translate with the step macro. And we say solve this maze. Now if you had tried to solve this maze initially, this is a simple maze, but what it was supposed to do is it's supposed to get from this location here over to this little red X on the floor. It doesn't know about these obstacles in the way. It has to find a path. We said, don't use any primitives. Just for the sake of argument, try just rotate and just translate. Rotate and step, those 2 macros we put together. It's got 4 states and 4 actions. And what you see here is the real learning response. This is it. You wrote the program in the context of this single trial. It notices things. It puts them in. Oh, we have one more controller I forgot to mention. There's a harmonic function controller, which is a path planner. And so it tries to go straight to the X, notices an obstacle, then it tries to circumvent the obstacle, and it does that recursively. And all the step and rotate have to do is figure out when it should be stepping and when should it be rotating. I'll play that again. It's got 4 states, 2 macro actions. I think I'll play it again. Yes, yeah. There's a forward-looking IR bumper. And when it sees an obstacle in front of it, it maps it into a configuration space. And then a new path goes around it. And then it figures out it's always trying to follow the path that exists with rotate and translate. So there is additional sensing. There's one additional path planning controller. And then the macros that existed already are trying to figure out how to get to those places.
And how does it know where the X is?
It was told. It was told, you want to be over there at XY, and you're here at XY.
Okay, so it has some kind of odometry.
The question is, how does it know where it's supposed to go and how it's getting there? It knew ahead of time where the goal was, and it's counting its own leg strides.
Okay.
So it puts its leg on the ground here, and kinematically it says, I just moved 3 centimeters.
Okay, so
And it does it again. Yeah, which was amazingly accurate, given we didn't expect it to be that good. All right, now my robot should run. Okay, now I'm going to leap into a new domain. This is grasping and manipulation. This is our platform Dexter that you see there. Right now what it's doing is running a schema that we call grasping schema. And the grasping schema applies little contact sensors at the fingertips of those hands to the object to try to figure out where all the forces are in the bimanual grasp. And there's a particularly compelling signature of a stable grasp. It's looking for that, and it's doing a gradient descent on a controller we designed to do that. Right there, it'll grasp it when it's finally happy with it. Now, and when it is, it's going to run a second controller in the null space of the first one, which is to kinematically condition the arms into a place where they're more comfortable. In the middle of their workspace, more isotropic. Once it gets there, it's going to do a twist test. It says, move it way over to your left. Subject to the grasp. Don't drop the grasp, right? Don't destructively interfere with the grasp. You've got to preserve it. The next thing is do another grasp in the null space of this grasp. There's another condition that it can formulate. It reparameterizes the grasp schema and runs that gradient in the null space of the original one, and then it can discard the first one, right? So what I showed here is essentially this transition, and there's 11 bits in this representation, still relatively small as a control representation. And all of these transitions are different places it can go that don't violate the condition that at least one stable grasp is present at all times. It learns the topology of this graph. It learns every one of these arcs has a parameterized controller that affects that arc. And now it can migrate around in this space. So if you say, pick up that object, don't drop it, do some manipulation to it to assemble it into another object, or hand it to an astronaut that you're working with or something like that, but do not drop it. It has to find a path through this structure. This is a very structured space, and it can learn almost online like our walking platform did. We allow the schema, which is down here, to start to build different operational contexts. So in this case, it says, well, if the object's too big, I should grasp it with 2 hands. If it's too small, I should grasp it with 1. And it can do that by stochastic exploration. Just say, well, there's the object I'm supposed to get. It has certain sensory affordances, scale, color, texture, that kind of stuff. And I can look for decision surfaces in that stimuli that would help me to allocate the procedural details at this point, right? So we learn how to generalize what we already know, have learned in a particular developmental context, to other contexts. I'll blow through this pretty quick. Having done that, this is what the robot will do. This is simple. Roboticists already know how to solve this. We can write the equations, but if the robot knows it, I claim it's better than if it has an equation for it. And so we'd like the robot to know it. What it's doing there is randomly selecting actions within a set that we permitted it to explore. And it gets an intrinsic reward for touching an object, for seeing an object, and then a bigger reward for touching the object it saw. And so it's randomly exploring actions, trying to get the most reward out of the system. So you see the object always stays within reach of its right arm. and it's doing the grasping thing, and there's no response, and then it does the vision thing, and it sees that. It figures out if it puts it together in this sequence, it gets all of this feedback response from the environment. So it learns essentially to touch what it sees. And this is a native reward structure, we say, is like dopamine. It's modeled after dopamine in the brain. However, that's pretty primitive. That's the greedy one, I think. It'll show you the greedy one in a second. But it's a simple when I present this to the machine learning community, what they say is, this is just trivial. Why bother us with this? This learning problem is too easy. And it is. It's too easy. It's not pushing the state of the art in machine learning. It's pushing the state of the art in programming. And the next step is to say, okay, that wasn't really a very rich problem you just learned. Your arms are only of a certain length. Whoops. How'd that happen? Oh. Your arms are only of a certain length. Learn when the objects are too far away for you to grasp. So it's using the greedy policy it already knows as a possible action. The sequence of seeing something, triangulating on it, reaching to that location, and closing its hand. Except now we're giving it objects that are a little too far out. This is like what a parent does when the child has already mastered something. You screw with their minds a little, right? You put it just out of reach and say, oh, now what do you do? It learns that it incurs a penalty for doing an action which is not rewarding. So it learns that it shouldn't reach to things that are out of reach. And so I won't let all that play out. These are longitudinal learning experiments that we do without ever stopping. So we do the first one, it gets a policy, we do the second one. This was done by a student in the lab, Shixiao Wu, over the course of a weekend. And he basically stayed up all night, 2 nights in a row, and trained it for 30 times on this, and then for 30 times on this, and got as far as he could. Right in our lab currently, we're trying to get through a contiguous year of developmental programming. Well, maybe a month first, and then a year. Because the software keeps changing underneath us. We make new decisions, we have to start over. One of the important things about this is that we have to make the software architecture stable so that the knowledge we get is all referred back to the same kind of architecture, or else if you pull out my nervous system in the middle of a longitudinal learning experiment, put in a new one, I have to start over. Vygotsky, a famous developmental psychologist, said that children learn how to point by, it's a gestural communicative act, right? They point to objects that they can't reach, even though they know they can't reach it, because if it sees another affordance in the environment, like that big blob that it sees moving into its workspace, doesn't have any very precise visual acuity, but it does see a big moving blob. If it sees a big moving blob coming into the workspace, sometimes it pays off to reach to things you know you can't touch, because they will change the dynamics and push it into your environment. And so this is an experiment in which he tried to do Vygotskian pointing, and the robot does learn how to point if there's a human present. If there's not a human present, it saves the penalty and doesn't bother. All right, so now here's the bottom line. After doing this for a long time, see if I can stop that, the robot has lots of knowledge. It knows how to pick things up and place them in new locations. It knows about the effect of scale on resource allocation. So this big object is picking up with 2 hands. The same grasping schema, instead of 2 fingers, it's 2 hands, right? That's it. This is picking things up on the table, putting them in that yellow bin is what it's doing. It also knows about handedness. Things that are on the right, it uses its right arm for. Things that are on the left, it uses its left arm for. So it's inquiring, it's making a query of the table. It finds another object which will satisfy the see and touch affordance that was also graspable with 1 hand, and it applies the right arm to go get it. And then it does the same thing. These are all just re-instantiations of the same general plan, the same general schema with different procedural details. I'll let this play out just to prove that he will go for that, and he will use the hand that he likes to use. So this robot can be told things. Please sort all the red things into that bucket, all the blue things into that bucket. I don't care how you do it. How you teach it, you just teach it red, left bucket, blue, right bucket. Do it any way you want, right? And that'll be the next thing I want to show. No, not that. Well, not quite the next. I'll go through these quickly because I'm running out of time. These are how it represents objects. Rob Platt, who's now working at NASA Johnson and the Johnson Space Center in Houston, is doing this for Robonaut, did this experiment as part of his dissertation, and he said basically with just a little bit of information in the schema idea and procedural details that we learn one at a time, he can now put all those grocery checkers out of business and build a $1 million robot that will do it for you. He learned about handles by the same method, except that a hole is a foreground object that has a background segment through it. And if you see that, it's particularly compelling as a reaching goal because the handle affords very stable and reliable grasping, and the robot learns that relatively quickly. And he goes on and does a whole bunch of other examples, but I'll go on. Now, transfer. If you have an architecture like this, it allows you to generalize. That's the whole point. It allows you to transfer as well. The mirror neuron story coming out of Rizzolatti's lab, and these two videos I'll show in a second, suggests that the status of a massively distributed control architecture is used in many tasks: recognition, differentiation, execution, communication in gesture and language, and programming. All right, so that's my definition of the mirror neuron story. It's somewhat provocative. That's not the last word. We'll hear more about it. But that's how I want to think about it now. And then let me show you what Rizzolatti noticed. This is a monkey who's had a recorder put on a particular cell in the somatosensory, no, in the motor cortex, right? And it's the cell that governs the pincer grasp. It's a region of cells, but they got a recorder on a cell. And you'll hear it when it grasps the food pellet. You'll hear a Geiger counter sound go off. That's the output of the audio from the recording.
Fanno un altro così. Come prima, tiri. Ancora.
Right? So they verified. Every time they give a food pellet, does a pincer grasp, you hear the recording. They got the right recording site inside the animal's brain. Now, this is the moment of breakthrough, and I believe this is very close to when they first noticed this. You can watch his expression if you draw your own conclusions. Something just remarkable happened just then. The animal isn't moving its muscles at all. It's watching somebody else do a pincer grasp. The same cell is going off. What they're suggesting, and that's the evidence that I'm using to justify this hypothesis. It's not just the somatosensory cortex. There's a large number of intercortical projections that take the sensation, the affordances of the food pellet, predict a pincer grasp would work. The visual affordances, the visual cues in terms of features and movements that it notices during a pincer grasp and associates them with the action of doing the pincer grasp and subsequently the reward of the food pellet. All of those things are causing that cell to, it's embedded in a very rich and cross-modal association matrix. And that's what they're recording. It just happens to be in the area of the cortex that's just prior to the motor circuit, right? So what this animal is doing is saying, I just saw you do that. I know how to do that. Maybe I'll try that. This is the basis, I believe, for all kinds of biologically plausible models of imitation, which is another form of programming, right? So if you want to teach somebody how to do something, you show them first. Why does that work? Because all of their own proprietary associations associated with that task can fill in the details that you're providing with the ones that they would be using if they were doing it themselves. And then they just replay that circuit, right? So we tried an experiment in which we had a teleoperator, John Sweeney did this work, program the robot. They said, here's a schema for picking and placing. If you look over here, this is a schematic representation of that schema. It has lots of contingencies, lots of transitions, but basically that's prior to the first localize with your eyes, and that's after the last time you touched the object and you left it someplace else on the table or something, right? And there's many paths through here that you could take. You see the teleoperator is not very good at this, but what's up there is a sequential diagram, and basically you're using a hidden Markov model to parse the transitions through that diagram. The robot notices, oh, you went from here to there. Its confidence that you're actually trying to demonstrate pick and place as a schema goes up, right? It doesn't know why you're doing it the way you're doing it. It just thinks you're trying to tell it that pick and place is the goal. So it puts the orange thing over there, and it's going to do the same thing with the blue thing and put it over there, but it's so much tedious to watch, and so just take my word for it. In the process of doing that, it says, oh, blue goes to, is a pickup reference, sensory reference for picking things up, and the bin on the right is the sensory reference for where I should put it down if it's blue. Orange is the sensory reference for pickup if it's the left box I should be putting it down in, right? And so all it does is it has this general background knowledge. It says these two things, very simple. One trial will show it. In general, that's not the case, but we biased the system so that colors were the things that it used to discriminate. All right. Now, this is the interesting thing. We tell it, okay, sort these objects in a manner that is consistent with what we demonstrated. And now the robot can play back all of that prior background knowledge it knows. Notice the bins are not in the same place. Notice the arm is not in this weird configuration that facilitates teleoperation. The robot's making its own decisions, saying, I would like to reach to it like this with my arm in this geometry. And by the way, I just did it with my left hand, although you never demonstrated that, because I prefer to pick things up on the left with my left hand. I'll put it in the bin that's on the left, even though it's not where you told me the goal was. This is the sensory affordance of the goal, not a spatial position itself. And so by teaching it using the schema transition model as the template that you can match to in a kind of a hidden Markov model, you can then say, yes, that is the right template. Here are the parameters that describe the implementation of that template in a particular case, and I'll play it back any old way I feel like. The robot's expressing its preferences in the matter and gets higher throughput, higher quality responses. All right. So now I've got to conclude here. I believe I have 3 or 4 more minutes. Mobile manipulation. This gets us back to the reason why we're visiting here in the first place, and this robot that I started the talk with. Mobile manipulation promises to project physical work into many of the places that information can now currently go. That is, if we allow computation and networks to act as a communication medium between robots and humans and robots and other robots, now we can put this in an elderly client's house, and it can take out the trash for them. It'll allow it as an embodied interface for human beings, medical providers, for instance, to interact with the client on a daily basis. It can log lots of data that is not being logged. It can do emergency response. And I want to close with some of the concepts that we've been trying to develop at UMass related to residential health care with distributed robots. And of course, my pitch is they're too rich and they have too many options, and you have to program them developmentally. You can't anticipate everything they're going to do ahead of time. You have to embed them, let them imprint on a client, and imprint on the client's environment and become good at the things the client needs. This follows after the NSF-NASA report on autonomous mobile manipulation that said that there's a huge market. They projected billions of dollars in market in as little as a decade related to manufacturing, logistics and supply chain support, agriculture and construction, space exploration, and residential healthcare. These are the 2 that I want to show some examples on. And they also identified the major challenges technically and otherwise to making this happen. One of them was funding from federal sources, and that's still a problem. But others were commodity mobile manipulators that could be disseminated widely so that people could learn how to do this first and then put them in the field to do the work. The other was programming methodologies for open environments. By open environments, it means environments that you can't possibly anticipate and predict ahead of time and then just write deterministic programs for them, or any kind of programs for them. So our effort here is in this U-Bot. This is a U-Bot 4. This thing on the table is a U-Bot 5, the next in the series. This is Patrick Deegan on the screen. There are the particulars. I want to point out a few things. It has a webcam, it has a screen, and it has a gaming interface on the remote side so that you can see, you can do a Skype conversation through the network with a local client who treats it just like a teleconferencing kiosk that moves around in space. But this one can point, this one can bring the voice of the person to you if you're not near the kiosk that you would normally use. It can also pick up things and interact in various ways that regular kiosks couldn't. This is an example of another graph that says you may not fall down. And basically it started in prone and it's executing this transition. And once it gets to this one, it's going to try to get to balancing. So these are constructions that result from this developmental programming paradigm, which are consistent with the other ones I showed you for bimanual manipulation and other things. This robot should protect itself. If it's trying to get over someplace, to pick up a bag or take out the trash, and you throw a book or a rock in front of it, it trips. It should take all the actions necessary to protect itself, those safety constraints that I was talking about before, restore its condition, and then continue with its task. And you shouldn't have to worry about whether that contingency will come up in a particular application or not. It should just be there. Background knowledge and common sense is a lot about what we're talking about in a developmental programming paradigm. Here's NASA asked us to take a look at a few examples. Now they want to land things on the moon again, and they want to build habitat. Well, whether it's the moon or the Mars, we're not really sure yet. They keep changing their mind. But the idea is when they went in the early Apollo missions, they had landers land near other landing sites, and they noticed that there's no gravity and there's no atmosphere. Nothing slows down. The blast from deceleration would throw regolith, lunar dirt, out in all directions, and it was very abrasive, and it would essentially scour all the metal off the facing side of the other landing site. So they want to land habitat modules, and these things here are what I want to call habitat modules. They're really paint buckets. We need to acquire them and move them. We need to assemble them into given configurations. We need a general purpose manipulator that doesn't have to presume terrain, gravitational field, the presence of other robots, the geometry of the final assembly. It needs to be able to be told these things and then be able to construct plausible and relevant, efficient motor programs for it. And so what you see here is that's the habitat module acquisition and placement idea. And NASA Ames is building a robot called Athlete, which is a big six-legged mobile manipulator to do some of these things. The other example is once you assemble the habitat into the right way, you have to berm it with regolith. That will insulate it from lots of temperature extremes. Actually, they're thinking about digging a hole, building inside the hole, and then blowing up a balloon, and then covering the whole balloon with regolith. Regolith mining and moving is important to them, too. If you mine just a few centimeters of regolith, which is very silicate-rich and oxygen-rich as a result, over about the area of a football field, then you throw it into some processes that remove the oxygen from the compounds that are in the regolith, you can supply enough oxygen for a crew of 4 for 6 months in just a few centimeters over a football field. So little robots, even this one that does it at this rate, could be entirely plausible as just autonomous miners that deal with the terrain and the crater structures and all that kind of stuff, and even optimize where they get the regolith from by the output of the chemical conversion processes. You don't need big mass production devices for a crew of 4, for instance. You just need a couple of these, maybe. You also have to berm the regolith up around the habitat module so that when they land new habitat modules over here, it doesn't scour all the front-facing metal off of the old ones. And so this robot, this U-Bot 4, has acquired a little tool which is like a bulldozer bucket. And it's both mining and berming a habitat. And that's what that one's about. Now, these are not the result of a developmental programming paradigm. These are concepts demonstrated by virtue of a remote teleoperator. Here are some other concepts related to healthcare. This is a family interface. So you see Adam over here doing a Skype interaction with Grandma, and his face is there, and they're talking, and you can take it by the hand, and it's a force feedback robot, and you can lead it around. You can show it the new flowers in the garden or the new pictures you got from, that kind of stuff. So you can increase the kind of social interaction between an elderly and sedentary, maybe housebound client and the rest of the family and the community. And you can also do it for medical services. I heard, if you see somebody fall down and it's inexplicable and they get up and they look okay, shake off their head and they sit down, one of the things you should do is you should immediately do a home-style stroke evaluation. You should ask them, just to move their facial muscles by saying some words, say some words that stimulates the linguistic centers of the brain, do some gross motion, and smile, I think. That's facial muscles, linguistic, and gross motion, right? If they pass, they're okay. If they don't, take them to the hospital immediately. Time is of the essence, right? So we had an example of this in my hometown where grandma fell down, they got up, they went about Thanksgiving anyway, and that night she died. Apparently had a massive stroke, not necessarily apparent by virtue of just, because you compensate. You don't want to be embarrassed. So you don't move your arm if it won't move, and you don't tell anybody about it, right? This doctor, who's our lab manager, Emily Harrell, gets into the robot here and does the stroke evaluation. It has the Skype interface, and you can observe what's happening. You can even demonstrate the motions you want them to try. That's the difference between an embodied interface and a kiosk. And the last kind of concept is, when does that person fall down as unresponsive? What happens then? And so what we've done is we put a digital stethoscope on the end of that. The doctor or the emergency medical technician applies the stethoscope, drives the robot, or the robot can do this by itself. There are fall detection events. They're out in the literature. We have one too. It can drive itself or it can be driven. It can apply the stethoscope, get a telemetry back to the EMT who's in the ambulance on the way to the scene, and have the neighbors alerted and all that kind of stuff. If you put this kind of device that can both be an information interface and have the potential for doing mechanical work remotely in response to external remote users or autonomously, you have saved a great deal of time and money in healthcare and allow elder clients to stay in their home a little bit longer. The last demonstration turns out 80%, I think I have these figures right, 80% of deaths due to household accidents are because of falls in elder clientele. And they might trip over something, and then they'll break a hip, and then they'll have complications, and they end up dying. So one of the things that you can do to improve the quality of life and safety of elder clients is just to clean up. Get their laundry off the floor, get inadvertent boxes off the floor. Here's a little mock-up of one that we did. On the left, you see our sensor array has modeled activities in a space. It knows the corridors by virtue of, remember those fees and the change in fees and those models, the activity modeling part. It knows that if you see a person here, they're going to head down the hallway in one or two directions. They don't ever turn and go into the wall, right? So it has activity corridors, and it's mapped them out for all the moving human objects in the environment. And that's supposed to be a depiction of it over there. Those are just places where humans commonly frequent. And then we had the UPS man in the form of Shiraj Sen in our lab come in and deposit a box someplace. The robot sees that that's in an activity corridor and generates a path plan like the legged walker that finds its way through a maze. It heads out over and pushes the box into a place which is outside the activity corridor and prevents perhaps a future fall. And these kinds of technologies are very simple. You won't want to build independent technology for each application. You want one application that will possibly do them all. And that's the important part. And here is the last slide, second to last anyway, which is some work that we're doing with Cynthia Brazil about the robot that you see on the table is going to be implemented in a much more sophisticated way using hands that were built by Jeff Weber at MIT and heads that were built by the Media Lab in collaboration with other people. And Digit Robotics is building the chassis like you see here on the table. And Zytomy is integrating all these pieces together. And the first one is actually being put together right at this moment. The head is not yet ready, but the hands are on, I believe. And this is very exciting. This will be a very expensive robot, but it'll be an unprecedented, I think, entry into social. This is called mobile, dexterous, and social robots, as per the Media Lab's primary interest. And finally, acknowledgments. We've got to do this work. We've gotten a great deal of support from DARPA and National Science Foundation. NASA's provided some support. ARO and ONR. And I should cite Microsoft has given us a little bit of money in order to develop an application for this robot as well. So thank you very much. All the people that are contributing are over on this side. And most of our lab, Cynthia Brazil, and two previous graduates from the lab. Thank you. I guess we have some time for questions, if anybody has any.
showed that bit where the robot was sorting, had learned to sort according to color, and you had the bins with different configurations, and you were saying it was picking it up with its left hand because it was on the left, and then the video kind of ended before we got to see what actually happened with the other ball. And I was really wondering what happened because that hand that picked it up wasn't going to be able to reach into the other.
Oh, I'm sorry, I stopped it there.
I was wondering if there was going to be some transfer movement.
We did that on purpose. Well, it didn't have enough common sense to really get to an integrated solution at that stage in development. So what it did was it went like this, and then it reached as far over to it as it could, and then dropped it there.
Oh, okay.
Then what happened is it started up another instance of the same kind of program, noticed that the right color ball was for that bin, was right there, used its left hand to get it, and put it the rest of the way in. And then later on, with more experience in that particular task, it knows that there's additional value because it can reach things across the center line. It doesn't have to be mutually exclusive. It knows there's additional value to, instead of just being a single-handed preference, if it's a pick-and-place task, if there's a single hand that does both the pick and the place, that's less costly than if you do this transfer move. And it learns that with additional stages of learning. You just have to give it training examples that point that out.
Thanks.
Yeah?
This is very nice. It reminds me, I'm not in this area, but it reminds me of work done one of the graduate at Rochester in the context of genetic programming.
Uh-huh.
They looked at whether you use primitives as a basis or use higher level abstractions, procedures like function call as a basis to composing new strategies. And I see in your context, the Markov models are the representation of your abstraction of more abstract actions. But you consider
yes,
other type of components.
There are a number of conceptually related ideas out there. Maya Matarik at USC has done it with subsumption architectures and behavior-based systems. She calls it a behavioral basis. As you noted, genetic algorithm, people use genetic GA solutions to certain subproblems and try to combine them into new ones, and through the mutation operators and all that kind of stuff. That's also used to some advantage by incorporating structure and incremental training, incremental programming and structure, and then reapplying it hierarchically. The main insight that we have is not in the sense that you can divide and conquer. That's been around for a long time. Our insight has to do with the conceptual similarity between something called an artificial potential and something called a value function. And they're both adaptively optimal. So once I build a program of programs, the resulting representation of that schema is precisely the same, has all the important properties to just call it a controller and throw it back in the mix. And by doing so, we can now take control actions, which are, and also the other big contribution is that factorability issue. That if I pull the artificial potential out and call that the intention, it describes a whole class of actions. And then I can dissociate it from the procedural details and attach them later. So yeah, there's a lot of good foundational work that suggests that this is the general way to go about these problems. We've just added a few little added benefits of our own with respect to our applications.
You're being modest. This is amazing stuff.
Okay.
How do
Andy.
you decide for what are the right common sense building blocks? I mean, do you do that based on the task that you think the robot's going to do and break it down into the logical subtasks, or how do you?
The role of the programmer is not gone in this system. It's doing autonomous learning, but basically it can be as ineffective as any program if it's randomly typed in at the keyboard today, right? So if you're a malicious parent and you teach it contradictory concepts, it won't learn anything. So that is an open question. In these sensory motor systems, the new role of the programmer is much more like being a parent. And it turns out that biological systems are also predisposed, pre-programmed genetically, to be relatively good parents. Mothers speak to their children in motherese. They raise the frequency, they speak in different cadences, and different sounds, and they evoke, they point a lot. What they're doing is they're pointing out the kind of sensory and motor references. They're appealing to the auditory channels that the child is most sensitive to, and they're basically being good parents without even knowing it, perhaps. But it in fact is a nice resonance between what the child's prepared to accept and what the mother delivers. And so programmers also have to think about how to be a good and effective programmer in this context. And we don't have as many answers there as we do architectural answers, at least beginning.
I wonder if that's partly because the parent's adapting to the child's behavior. I mean, like, you know, when you get, you're getting your own dopamine kind of response when your child kind of
smiles,
to you.
yeah. Yeah, there's definitely, there is both the role of child and the role of parent in the gene pool when we're born. And eventually, if development goes as normal, we'll be in a position to anticipate how to deliver control knowledge to another copy of a human being at some point in the future. So being a teacher and being a student are very related activities. And unfortunately, these robots are very different than the human programmers that will have to deal with them. So we have to kind of adopt a new strategy, figure out what works. Now, the interesting thing about it is that you could resort just to stochastic, you could just give it a structured space and say, I don't know anything more about this, go at it, explore. It's possible that that will yield some interesting robot behaviors that are not human in conceptual structure. Those robots can then act as teachers to other robots, potentially, one day. We can't do it yet, but it would be nice. We're now trying to see all those bimanual activities that you saw with Dexter. Of course, he has fingers and everything, but when he's doing big objects with two hands, this robot should be able to do the same things. So we're trying to see now whether Dexter can actually either just port the software in schematic format into this robot and have him search just in the procedural details, not in the schematic details. Or whether perhaps there's a way for the robot to actually conceive of a simple example, like the teleoperator did in that other case. I'm going to show you this ball goes here, this ball goes here. Now do whatever you want and solve the rest of the problem. Maybe Dexter can actually serve as an instructor or a programmer for this robot as well. It's not in the short term. All right? If there are no other questions, thank you very much. And as I was saying before, this robot should be running around in the hallways later this week, so keep an eye out. And the people that are responsible for most of the work are in the audience. If you need an introduction, let me know.